Hi there, this is a presentation for Tau-Beta-Pi about a quick primer on hardware prefetching and memory access patterns. This work will basically be a short introduction to the concept of hardware prefetching, and will also go over a few commonly used memory access patterns that hardware prefetching algorithms may have to go over. So the first question that we will be attempting to answer is, what is hardware prefetching? What is hardware prefetching? So, in its essence, hardware prefetching is a common method for effectively hiding long memory latencies in modern processors. Um, Memory accesses take a large amount of time and often keep a stream of work from reaching its conclusion while waiting on the data that it needs in order to conclude. Prefetching is a hard prediction problem. The search for prefetchers that can accurately capture several different kinds of memory access patterns is still an active research area. So basically, most modern processors need frequent and quick memory accesses for several kinds of workloads. And if those memory accesses take a lot of time, then those workloads cannot complete in a quick and effective manner and will be memory bound, that is, waiting for memory instead of actually spending that time processing. So, as the performance of processors increases at a faster rate than that of the memory hierarchy, this memory bottleneck is becoming more significant. That is, processors often encounter performance problems due to long memory load and store latencies. So, the cache hierarchy generally is composed of L1 caches or level 1 caches, which are the closest to the processor, level 2 caches, which are one level further removed and could have a couple of processors that they service, and L3 caches, which often are also known as last level caches, which serve most of the processors in a processing unit. So in the case of a L1 data cache miss, data must be fetched from lower level caches or even main memory, which can take potentially hundreds of clock cycles depending on the structure of the memory hierarchy. So in order to sort of reduce this performance impact, most high performance processors utilize hardware data prefetching techniques to effectively hide the memory latency and thus boost performance. So how is this long memory latency uh, for memory-bound compute workloads hidden? And it's basically hidden by predicting future memory addresses that need to be accessed and issuing memory requests for those cache lines preemptively or ahead of time, so the data is already present in a higher level of the memory hierarchy, which in most cases is the L1 data cache when it is needed by the program. If the accuracy of the prediction is high, then in most cases the memory latency is hidden. However, a potential pitfall exists. If the prefetcher does not make accurate prefetch requests, then several problems can arise. Inaccurate prefetches increase contention for available memory bandwidth and waste cache capacity, which in turn can result in additional cache misses. This means the prefetching mechanism is actually wasting energy and cache capacity in doing work that is actively making the performance work. So this is definitely not a scenario that uh, uh, a hardware prefetcher should ever should try and avoid this scenario at all in all cases. So basically, at its core, hardware prefetching is a problem of prediction. We need to predict which cache lines will be used next and place it in the cache before it is used. That is requested by the processor in order to execute its workloads without hitting long memory access times. So very briefly, we will go over the types of memory accesses next. So there's three main types of memory accesses. The first one, well, let me sort of cycle back. The reason why we're going over memory accesses is to basically try and develop an idea of how difficult the prefetching problem is. As we mentioned, the prefetching problem is a problem of prediction, and the problem with that prediction is we're trying to predict ahead of time the memory accesses that might be needed. And in order to do so, we have to analyze the types of memory accesses that the processor has to go through. So the first one is a regular data access or a regular memory access. This type of memory access is a common one wherein data is arranged sequentially, like an array of data or an image. Each address that is accessed is sequential, and in this case, prediction is relatively simple in the scenario because if you're going after address x, then the next one is x plus 1, x plus 2, x plus 3, and so on. The next one that we would like to go over is an irregular memory access. So in this case, this is also a common type of memory access, but in this case, the data is arranged randomly and sparsely, like several pointer accesses. So in this case, each address that is accessed is random, and prediction is relatively difficult, as you can see in the image, where we have two addresses that are accessed, and the next one is some arbitrary amount of memory accesses later, and the next one is again an arbitrary amount of memory accesses later. So this is a little more difficult and not quite as simple as just sequentially uh, getting the next memory address. The last one is a mix of the two. So a mixed memory access is basically a type of memory access which is a frequently used one wherein the data may be arranged randomly and sparsely, like several pointer accesses, but each pointer access also has some sequential access. So an example of this is a data structure such as a linked list of objects. Each address that is accessed is random, but also sequential in bursts, and prediction is also relatively difficult in this scenario because unless you do know ahead of time that, hey, this is a memory object that may be sequential in the near future, but random in the distant future, it's something that's difficult to predict. And in any scenario where a data structure that is non-contiguous, such as a linked list, is used, this type of memory access is the norm. So very briefly, that was a quick primer on the concept of hardware prefetching, and we also covered some types of memory accesses and why that makes a common algorithm for hardware prefetching a little difficult. Yeah, thank you for your time.